Hi, my name is Andy Zimmerman. I'm the CTO here at Grace Technologies, and I'm going to spend the next roughly 45 minutes kind of talking with you guys about one thing that's become incredibly important in the industrial environment, and that is how we can use new technology to monitor the rotational assets that are just incredibly important to basically everything that happens in that space. All right. So I'm going to make a few assumptions before I kick off here about why you're coming to this presentation and why this topic is important to you. First and foremost, I'm going to assume that you believe or have some reason to believe that 24/7, always-on vibration monitoring can help you better maintain at least one rotational asset in your facility. Secondly, I'm going to assume that you'd like to build your 24/7 vibration solution around an existing PLC-based infrastructure. We'll kind of talk about that in great detail later. And lastly, I'm going to assume that you're somewhat concerned about the cost of putting in a PLC-connected 24/7 vibration monitoring system specifically for those assets in your facility that are maybe not highly critical. So in other words, if we want to monitor all 1,000 motors in a given location, can we do that affordably and in a way that is going to allow a value to be derived by the investment in the vibration monitoring technology? So today we're going to cover kind of 5 main topics. The first of which is just the bottom line, why vibration monitoring is important in the industrial space. I'm then going to talk about kind of the fundamentals or basics of what vibration monitoring is and how we use it, and then talk about how PLC integration can bring data from the vibration world into kind of the standard maintenance procedures in an industrial facility to create some tremendous value. From there, we're going to talk about new technologies that have come up in the IoT world, the Internet of Things world, and how those can be used to do 24/7 vibration monitoring. And then I'm going to bring all that together by bridging those new technologies in the IoT space together with kind of the existing PLC-focused environment that we see in most industrial facilities. So why are we at Grace Technologies presenting on this particular topic? Well, we've always come at our industrial Internet of Things line from a very industrial perspective. Grace was founded back in 1991 by Phil Allen, who you see here. We just actually transitioned into a second generation of family-owned leadership as Drew took over as our CEO in January of this year. We've spent the last 20 plus years, I think 25 plus years now, as a Rockwell and Compass partner. And over that time, we've established ourselves as a leader in the industrial side of the electrical safety space. So anytime we talk about a project, whether it's IoT or otherwise, we're always kind of coming at it with a deep background in the industrial world. On the other hand, our development of our IoT products has always come from a very application-driven perspective. So our wireless vibration monitoring products that we have in our predictive maintenance line of technologies were derived originally from research funds that came from the Department of Defense, the National Science Foundation, the Department of Homeland Security, and also the United States Department of Transportation. And through these grants, we've actually applied our technologies to a lot of different applications, right? From long-span bridges to wind turbines to burning or damaged structures. And then most recently and most pertinent to this particular discussion, we've taken that same technology that's worked elsewhere and we've applied it to industrial equipment in an effort to kind of make it tie in as closely as we can with that industrial space. So from here, I'm going to talk about why monitoring vibration is important at all. Right? So let's start with just equipment monitoring generally. We're not even talking about vibration here. Why should we monitor our equipment? Well, the big reason is that monitoring an asset in an industrial facility allows us to reduce unscheduled downtime. Right? If we can detect a defect before it causes a piece of equipment to fail, it allows for our maintenance to be planned instead of reactive. And this allows us to reduce our maintenance expenses because as we're detecting degradation early, we allow us to do maintenance in an earlier fashion, and that reduces the severity of the issue and thus the cost of repair, right? And one of the things that we really like to focus on at Grace, because this really gets to the core of who we are as a safety company, is that when you're eliminating or drastically reducing reactive maintenance, we're also increasing worker safety. And the number that we like to point to there is 70% of your workplace injuries are going to happen during reactive maintenance. So if we can deploy IoT or other predictive maintenance technologies to help reduce reactive maintenance, we can also prevent accidents from happening in your workplace. So now, why should we monitor vibration specifically? And many of you may have seen this particular diagram, usually called the PF curve. The bottom line behind monitoring vibration is that it lets us see issues in equipment earlier than with some other kinds of monitoring. So, if we do nothing and we're just waiting for that equipment to fail, right? We're gonna start at kind of the bottom end of this curve. We're gonna give ourselves no time to prepare for that failure. If we're kind of paying some attention and we notice that that piece of equipment is starting to smoke or get louder, this human sorts of detection is going to give us a little bit of time, but not a considerable amount. Then if we start laying sensing capabilities in there, like monitoring temperature or current, we start to see an increasing amount of forewarning before that piece of equipment fails. And now at number 3 on this chart, we start to get to what we're talking about today, which is low frequency vibration. And then we get into the kind of the higher frequency vibration spectra. And then at the very high end of this is leveraging all of those pieces to do predictive analytics. So the bottom line, why we're talking about this topic today, is that, if we're monitoring vibration on a rotating asset, it gives us a really good chance of creating a significant amount of time between when that defect starts to occur and when it causes that equipment to go down. And obviously, I guess the last thing on this slide is that, the earlier we detect it, the cheaper it is to repair. So there's an advantage to that early indication, right? We have lower downtime numbers, we have lower costs of repair, and ultimately we end up with safer maintenance activities. So once we've got a monitoring system in place, what can we do with it? Well, we can leverage that vibration monitoring system to detect, trend, and classify a bunch of different types of degradation. But specifically, we're looking at things like misalignment, unbalance, looseness, things with bearings or gears that might come up. And these can be applied in a lot of different ways on a lot of different types of assets, from motors to pumps to fans to compressors and the like. We can kind of extend this kind of classical definition of vibration analysis to look at detecting and trending degradation, things like cracking, material softening or hardening, and we can apply these to more structural systems like cranes, supports, footings, that sort of thing, and to equipment that's been subjected to impulses, things like AGVs or press, kind of stamping press type operations. We're not going to talk a lot about that today, but you can leverage vibration to do this sort of predictive maintenance. So what can't we do, and what's kind of outside of the scope of what we're discussing today? Well, vibration monitoring, at least in the traditional sense, is often hard to apply to low run speed applications, where you're trying to look for either failure of that low speed rotation or some sort of indicator that lubrication needs to be modified or fixed. So we often leverage an ultrasonic or ultrasound based monitoring system in the high frequency range to do this sort of monitoring. So that's kind of outside of the scope of what I'll be talking about today. We also can't really do high-speed machine protection. So what we're talking about today is not applicable for scenarios where you're trying to shut a piece of equipment down very quickly when something catastrophic happens, like a wrench gets thrown in the fan or the mixer. We're also not going to talk about non-continuous rotating equipment, so a CNC machine or something that's on and off and on and off. Rotating equipment with unknown shaft speeds. So if you have a variable frequency drive without a tachometer, for example, we're not going to talk about structural systems like I mentioned on the last slide, or impulse or impact loading scenarios. So that just kind of paints the picture for the rest of the talk today. So from here, let's talk about, how we actually get about monitoring vibration. In the context of rotating equipment, which is where we're focused on today, everything starts with the shaft. right? If everything's healthy, this pillow block bearing shouldn't move at all. That shaft's just going to spin nice in there, and there's not going to be any vibration happening, right? But if we introduce some sort of small defect, in this case, we've got a little bit of unbalance added, right? That pillow block is going to begin to displace, and that displacement, can be measured in a displacement value, which comes in usually in the case of an inch or a millimeter, right? We're measuring it in units of length, right? We can also look at that change in displacement, and we look at that in terms of velocity. So that's the speed with which this thing is actually moving, right? That's inches per second, right? And then we can actually look at the change of velocity, which is an acceleration measurement. And that we typically monitor in inch per second squared, or G. So when we talk about vibration, we're talking about any one of these three things. It's the displacement, the velocity, or the acceleration that's experienced by an asset, in this case, this pillow block bearing. So how do we measure that? Well, we can go straight at displacement in a variety of ways. We can use a potentiometer, an LVDT, a non-contact optical sensor, any of these things, but they all require a stable reference point. They're often hard to install and maintain, and they're typically really bad at high frequency. So we typically don't monitor displacement directly when we're looking at vibration. We can use velocity-specific transducers, typically piezoelectrics or LVDTs. Geophones are popular monitoring ground vibration, but these direct-to-velocity measurement devices are typically expensive and hard to miniaturize. So what we typically use in a vibration monitoring, application is an accelerometer. These MEMS or piezoelectric-based transducers are inexpensive. They're easy to make, pretty small. And they allow us to capture acceleration data, which then can be numerically integrated and converted into a velocity measurement or a displacement measurement. So this is what really lets us get at that balance of plant application, where we're using low-cost sensors to get sensing capabilities on maybe all of the bearings in our facility. Okay. So once we have this in place, right, how do we actually figure out that something's going wrong? Well, there's a lot of different parts to that, but the way this kind of plays out, and I'll use this simple graphic here to describe it, is you have a defect. In this case, that unbalance we talked about earlier, right? So that shaft is not spinning totally perfectly, and that's causing a vibration of that pillow block bearing. The accelerometer that we placed on top of this pillow block is going to convert that acceleration into a voltage, which we're then going to take into an analog to digital converter. That's on the sensing or processing kind of component in the system. And that's going to make that analog signal available to the computing parts of the system. It'll then be analyzed and used to either display in a graphical form or to issue an alert to your maintenance team. Whatever. This is the very, very high level view of how this works. So the question is, does the amplitude of that signal that we're measuring from that shaking system matter, right? Does the amplitude of that actual signal, is that indicative of anything when we're monitoring it? And intuitively, yes, obviously, if it's shaking more, that is a worse scenario. And we can prove that out here because amplitude is almost always indicative of the severity of a defect. In other words, a bigger defect will lead to a larger vibration amplitude. So if you see here, I've got a relatively healthy situation here with this bearing, right? And it's vibrating a little bit, but not very much. If I induce a small defect, I'm going to see an increase in that amplitude. And then if I further increase the size of that defect, you're going to see a larger wave still. So this is all very intuitive, but I want to just lay this out as a foundation for what we're looking for. Because it gets a little bit more complex than just this. You can't just look at the amplitude of a signal. We actually also have to pay attention to the frequency of that signal, because the severity of the defect that we're seeing is going to matter depending on the frequency of the signal that's put out. And I'll kind of walk through that in these next few slides. So for starters, I'm going to provide kind of a simple experiment here. We have two bearings that are undergoing identical displacement. Okay, but one is experiencing that displacement at a significantly lower frequency. Okay, so I'll turn these two motors on, if you will, and you can see one of these two things looks a lot worse than the other, right? And the bottom line here is that high displacement is going to be more damaging at high frequencies for reasons like you see right here, right? Now, if we move on and look at acceleration, right? So we now have these two bearings are experiencing the same acceleration at different frequencies. The one on the left is a low frequency. The one on the right is high frequency, okay? So I'll turn these on. All right, so if we're looking at this, the one on the left here at low frequency looks a lot worse off than the one on the right. And the take home here is that if you're looking at acceleration, that's more damaging at low frequency. So it's kind of the opposite, right, to what we just saw in the displacement sense. So now I'm going to do the same experiment. These two things are experiencing the exact same velocity, but at different frequencies. So again, low frequency on the left, high frequency on the right. So let's turn these on. So this starts to become a little bit less clear which of these is more severe. And the reason for that is in the velocity domain, that severity is relatively constant across all of the frequencies that we experience. And the take home from this is that, high velocity is actually equally damaging across frequencies, and that makes velocity a really important parameter to monitor when you're looking for damage in your rotating equipment. And this very reason is why when you look at the standards that reflect best practices for vibration in the industrial setting, those are all based on velocity-based amplitude alarms. Right? So I'm not going to get into this a lot here. There's a whole, set of other courses you can take to get into the standards-based approach to this. But the bottom line is that, as that velocity increases, it doesn't matter what kind of machine it is or how fast it's spinning. If you see a velocity over roughly, 0.3 inches per second, that's usually a damaging scenario, right? So we've talked a little bit about frequency from the perspective of, this matters depending on how you're monitoring, but it also allows us to indicate the type of defect that we're looking at. And I'm not going to talk a lot about this here, but this gives a simple example of how this might play out, this graphic you see here. So if we have an unbalance taking place, we're going to see that unbalance at 1 times the shaft speed. So every time that shaft rotates, we're going to experience 1 cycle of that defect, right? Whereas if we had some sort of issue with one of these fan blades on the fan, we're actually going to see that turn 8 times every time that shaft spins, right? So we typically break our frequency domain response of this rotating asset into a number of different bands. And the ones that I'll focus on today are subsynchronous, which are less than the shaft speed, synchronous, which are going to occur at that shaft speed, harmonic, which occur at multiples of that shaft speed, non-synchronous, which are going to occur, these are things that occur at ratios that aren't really triggered by that shaft speed. So this can be things like your bearing, it can be electrical noise, these sorts of things. This would actually occur also with looseness. You might have a harmonic that's occurring based on the structural system, not the rotational speed. So that's another band. And then if we look at kind of the high frequency modulation that occurs above that band, we start to really focus in on gear and bearing situation. So it really matters where that defect is occurring. We'll get a different signal. And you'll see this a lot clearly in the next few slides here. So how do we measure this frequency? Well, first, same thing we did before. We're going to put an accelerometer on the asset. We're going to capture that data and convert it from analog to digital form, put it into a processor. So that digital form allows that processor to deal with it. It's then going to convert it from acceleration to velocity because of the reasons that we just talked about. And then it's going to take that velocity data and move it into the frequency domain using what they call a Fourier transform. Right? So here's kind of an example of how this works out. So we've got our acceleration data here up at the top. That's coming from, in this case, we have a damage that's happening from unbalance that's at the shaft speed, and we have damage from, say, a chipped blade that's happening at 8 times that shaft speed. So those signals together in the acceleration domain look like this one on the bottom. Okay? I'm going to put that through my processor once I've captured that data, and I'm going to convert it numerically to a velocity signal. So now instead of units of G, I have units of inches per second. All right. And then I'm going to do a Fourier transform, which is in the parlance of the processing environment, this will be a discrete or a fast Fourier transform. It's going to bring it into the frequency domain it's the frequency domain, which lets me look very specifically at the frequency response of that accelerometer. And you can see very clearly here that we have a peak at 1 times the shaft speed and a peak at 8 times the shaft speed, which is exactly what we'd expect to see, right? So if we have a damaged situation here with this asset, you're going to see these 2 peaks. And if this was healthy, there'd be nothing on this plot. Okay? So I'm guessing everyone in this room has seen this before in one way or another, but if nothing else, you've seen it on your home stereo, where you have a graphic equalizer that's going to break your audio output into frequency bands. So your bass is happening at the left of this graphic EQ, and your treble is at the right, right? And it's broken up depending on the frequency of that signal. We're not doing anything differently. That's basically what it is. So when we're monitoring your rotating equipment, we're pulling bands that associate with different defects, and we're just looking at how much power or how much amplitude is present in each of those frequency bands. So we end up with a chart that looks like this, and if you start to see spikes in different bands, that can tell you, something from, we've got an eccentricity issue to, oh, this is actually probably a bearing issue or a gearbox issue. And so this is how we take that raw acceleration signal and we start to drive in on actual vibration problems. So here's an example. This is a plot of some actual vibration data. It's kind of complex to look at this 3-dimensional plot, but we're looking at frequency on this bottom right axis. So as you get further to the right, it's higher frequency information. And as you go up the left axis, that's over time. So if you look at this, we can kind of see that over time, at the beginning here, we don't see much in the way of signals, right? But over time, there's going to be an overall increase in amplitude, right? Like just as you proceed across time, stuff starts to happen, signals start to prop up, and that's telling us, hey, some problem is occurring. But then if we dig into this plot in a little bit more detail, we actually see that kind of in the mid-range of this, that between, between 3.2 and 12.2, which is hyper-specific for a reason, just tells us that this is a bearing-related problem, most likely. Okay? And then if we dig in even further and look at the shaded sections of this, you see that these narrow red bands are occurring at multiples of about 3.2 times the shaft speed. Right? And that in this particular bearing is going to tell us, hey, this is not just a bearing issue, but this is a outer race issue inside that bearing. Right? So this is at a very high level and a very fast level how vibration analysis works and why we are interested in deploying, either PLC or IoT-based vibration sensors on rotating equipment. All right, so the key takeaways from this vibration primer, and I apologize for those of you who've been through this before. I know this is kind of a very ground up approach to vibration, but these are the key takeaways, right? Vibration is important because it lets us see defects earlier than we can with other sensing types. All right? Vibration amplitude is almost always indicative of the severity of a defect. Vibration frequency can be used to help us narrow in on the type of defect that's creating that amplitude, right? Accelerometers are often the best way to monitor vibration, largely because of their cost. So keep that in mind as we talk about IoT. And velocity, not acceleration or displacement, is important because it lets us see defects at all frequencies, independent of what the rotational speed of that system is. All right? Okay, so that you're now all experts on vibration. So we're going to move on to the third topic of this presentation, which is taking that framework that we've just created and applying it to an industrial facility using kind of PLC-based standard industrial protocols, right? So historically, vibration monitoring has been done by trained vibration analysts. Right? Somebody who's going to actually physically walk through your facility using handheld equipment and take measurements. These measurements are typically collected on, say, a monthly basis or a quarterly basis. and then they're analyzed as they're collected for defects, right? Did we see a spike in the bearing band? Did we see an increase in amplitude, associated with the run speed of that particular piece of equipment? And then that data is captured once per month or once per quarter and looked at over a period of time to see, are those amplitudes increasing? And those can be indicative of problems. Now, clearly, if we're doing that instead of monthly or quarterly, we're doing that, say, once per hour, that's going to allow us to detect faults earlier. And that earlier detection is going to give us all the benefits we talked about at the top of this presentation, right? It's going to allow you to save money on downtime. It's going to allow you to save money on maintenance, and it's going to prevent workplace accidents in your facility, right? But it's also going to give us the ability to make that data readily available to anyone in your facility via standard industrial methods. In this case, we're talking about a PLC. So, rightfully so, over the last couple of decades, there have become available, many different options for monitoring vibration in a 24/7 manner using a PLC. Rockwell has, tremendous offerings in this space. You can buy accelerometers from them. You can buy, I/O from them that will hook up to your PLC, and then you can buy software to actually bring all that through the PLC and into an environment that's going to let you issue alerts and alarms and do all the things that you want to do for your facility. Okay, that's a great investment in most cases for critical assets. But what we're talking about today is actually that balance of plant. Like, how do we get that technology on every single motor in your facility, not just, the main exhaust fans or whatever it is that's critical to your operation, right? The problem with these PLC-based methods is that they're just too expensive in most cases for these balance of plant installations. That's driven by hardware cost. Sensors are expensive to start with, but when you start adding in cables and the I/O, the PLCs necessary to capture this information, you're displaying it on HMI, you got to buy software, it adds up. And if you're doing a wired, tethered installation, which is typically the case if you're going into a PLC, these add expense just by running conduit and all the typical things that go with doing any sort of wired installation in an industrial environment. So it's become fairly self-evident, I guess, over the last 5 years that IIoT-based, so Internet of Things-based vibration monitoring is really important for the industrial space, right? Because A, it's wireless, and as a result of it being wireless, it's easy to install. And that also will drive the costs of the whole system down and allow us to deploy not only on our critical assets, but on our non-critical balance of plant assets. So, this brings us to the fourth main point of this presentation, which is to talk a little bit about how wireless industrial Internet of Things vibration monitoring can be put into practice. Okay? As we've discussed, IoT technologies in recent years have really revolutionized vibration monitoring. They've taken us from this perspective where you need to have a really expensive cabled system and moved us into a world where we can quickly deploy vibration sensors on pretty much anything. These are low cost, usually MEMS or piezoelectric based accelerometers that are integrated with a wireless component, and as a result allow us to have low cost hardware that can be coupled with low cost web-based software to deliver vibration information readily to a user via the cloud. Right, so we're typically battery powered, which means these devices are, self-contained and can be usually magnetically deployed on a motor or a bearing or wherever you're putting it, just by literally plugging the battery in and plopping it down. Right, and that's a lot easier than kind of the status quo of a full installation with conduit and what have you. So to just reiterate what we've already talked about, right? A wired accelerometer, those are great. They have super reliable communication. You can push a ton of data through them. They're wall powered, but they're expensive to install. So when IoT came along with the promise of wireless, inexpensive to install, magnetically installable hardware, this is really exciting, but it's actually driven a couple of unforeseen complexities. So first of all, you're going to see significantly less reliable communication. Anytime you're dealing with wireless, not every packet is going to get through the way it does when you're tethered together. It's also going to have limited bandwidth. And we'll talk about that a little bit later, but that means you can't push all that acceleration data through. You've got to get around that in some other ways. And oftentimes these IoT-based vibration sensors are battery powered, which, I know as well as you, changing batteries is not a fun proposition, right? So what has happened in the IoT world to kind of counteract a lot of this is, we at Grace and others in this area have started using embedded processing techniques to increase battery life and decrease the demand on that wireless bandwidth. So, when you look at it, wirelessly sending raw vibration data is not feasible. Typically, in order to do the type of analysis that we talked about in the early section of this presentation, you need about somewhere between 1,000 and 100,000 data points to be collected in any one vibration cycle. So this means, if we want to get data once per hour, I'm going to have to send, probably around 10,000 data points every hour in order to do that analysis. And we typically don't have enough wireless bandwidth in a facility to send this from, say, 1,000 different motors. And additionally, if you're doing this once an hour, sending all that data wirelessly is actually going to draw on that battery pretty heavily, and there's no way you're going to get the 3 to 5 years of battery life that we really want to see from these IoT products. So by focusing on processing data before we send it, we can actually allow these Internet of Things-based devices to work 24/7. So the way this typically works is that banded analysis we talked about, where you break things down into individual bands, that actually can be done right on the device itself, right? So your sensor's there, you got a processor there, it captures that data, it processes it down, and it breaks it into these bands. And if we do that all on the sensor, instead of sending 10 or 100,000 data points per cycle, we can send, in the case of Grace, we send 65 data points per cycle. And that gives us the ability to reduce our wireless footprint, which is great from the bandwidth perspective. And it also really allows us to extend those battery lives into that, 3 to 5 to 10 year range, depending on your settings. So, another advantage of IoT-based software is the use of the cloud, right? We have typically in any industrial Internet of Things-based system, we have a cloud component. And this, has all of the advantages that you'd expect from anything that's cloud-based. It's low cost relative to licensing, a piece of industrial software. There is no internal hardware needed. You don't need to spin up a server in your facility. It's all there. You just click the button and it's turned on remotely, right? It's going to give you easy access both to the real-time data that's been collected in the last, hour, but also the historical data. You don't need a SCADA or a dedicated historian. That historical data is all there because it's sitting in a cloud-hosted database. Okay. Additionally, if you look at the scope of the IoT world when it comes to vibration analysis, you'll find that most artificial intelligence or machine learning based techniques that are kind of coupled with our vibration analysis hardware, those are typically cloud-based. And this allows us to constantly evolve our analytics, right? As we get better algorithms or as we collect more data, we can immediately drop that into our analysis packages that sit on the cloud and let those analysis packages evolve as we learn more and as we get better at doing that prediction. And pretty much all vendors of IoT software use this ecosystem. The problem with that in the industrial environment is that cloud piece doesn't always play well with the PLC. And it's vitally important, I think, and pretty much all the customers that we talk to, that they kind of confirm this. It's vitally important that if we're going to do IoT-based vibration monitoring in an industrial facility, we have to be able to get that data, or at least the process results, back to the PLC so it can work in the same paradigm as the rest of those industrial systems. So, the last part of this presentation is going to be focused on, all right, how do we bridge that gap? We've got this great technology that can produce these great benefits, but how do we get it to work in the industrial facility, specifically with a programmable logic controller? Okay. So this slide is going to show you what I would expect to see in any industrial Internet of Things deployment. Obviously, this is our Grace branded product offering, but this could be anything. Any provider of an IoT system is going to look somewhat like this. You're going to have vibration sensors down at the bottom left. Those sensors are going to be pushing data to a gateway of some sort, and that's going to take that data up to a cloud. And then that data, once it's in that cloud, is going to be made available to you for visualization, analysis, reporting via some suite of web or mobile applications. This is the standard IoT deployment, right? Now, contrast that to the standard controls-based deployment, where we probably don't have wireless sensors. So we can kind of take that piece out. We got some sort of tethered accelerometer that's going into, a DCS or a SCADA or a PLC. There is no cloud. There is none of this other stuff. These are two very different worlds. So the question really for the rest of this presentation is, all right, we know this is important to do. We know we need to get that vibration data captured, and we know we need to get it into that PLC. How do we do this all in a way that's affordable and that makes sense for the balance of plant kind of asset? Okay. So there's a lot of different ways that could be investigated for doing this sort of thing. I'm going to discuss 3 of them today. These are not, the only 3, but we'll talk about all 3 of them and then really hone in on that last one, which is the industrial protocol. So the first of which is the use of an API to bridge that gap. Okay. The way this is going to work is you're going to have your cloud system on the left, and it's going to expose an API, usually RESTful API if you speak that lingo, to the PLC. And that PLC then, using a cloud connection, is going to ask for data from the cloud. Okay. This is great in that it's flexible. It's easy to deploy. It's pretty universal. These RESTful APIs are usually designed very similarly, but it's limited from a support perspective. You typically can't just go get a PLC that's going to do this. You have to have a specific cloud-enabled PLC. You cannot roll this particular solution out if you have to be on-prem. Anytime you're doing any sort of API integration, you are fairly regularly going to have to look at updating that. So you need third-party support continuously. And it does expose your facility to some security risks because you are kind of directly connecting your PLC to a cloud resource. So in some cases, this is ideal, but it's kind of not the focus of the talk today for the reasons listed here. So the second approach is to use a broker. This could be MQTT, OPC-UA. There's a variety of different protocols that sit in between here. And the idea here is that either your gateway or your cloud is going to provide data to a broker, which is then going to make it available to the control system. Okay? This is, again, a great option in a lot of cases. It's interoperable. These MQTT in particular is designed to allow different systems to connect together relatively easily. They're generally pretty secure because they create that broker barrier between the two end pieces. Both of these standards, MQTT, OPC-UA, are becoming more widely accepted. But again, PLCs don't necessarily like to talk that nicely to a cloud-hosted broker, especially if it's a legacy PLC. Each system that's designed is going to be unique, so it requires upfront work to bridge that gap for each different system, each different type of sensor. And, as you go to expand to the next system and the next system, there's limited kind of maintainability support for this type of ecosystem. You really need somebody in-house who can manage the complexity of that broker and tie your systems together for you. Now, certainly a valid approach if you have a good system integration setup. But in a lot of cases, especially with older facilities that have legacy equipment, maybe not the easiest way to bridge this gap between IoT and PLC. So what I'll finish the conversation today talking about is bridging this gap using a standard industrial protocol. In this case, we're going to focus on Ethernet IP. Okay, so the benefit, in here, actually, let me go back one slide. So, what we're talking about here is we're not losing any of the advantages of either side, right? We've got a cloud completely set up. All that data is going to the cloud if you want it to, but we're also exposing out of this gateway a parallel Ethernet IP hardwired connection, right? So we got 2 separate kind of gateways to the vibration data. It's going through that gateway and it's being made available to both of these sources. Okay, so that's important here. The benefit of using these industrial protocols is that in the industrial environment, this sort of thing is going to be the most widely accepted and widely understood mechanism for getting data into a PLC. It's tested and proven. All of your devices are going to connect over some industrial protocol that's going to provide you with secure communications. It's going to enable an on-prem type deployment if the cloud is not an option. It's going to do just a lot of great things for making this IoT-based vibration data flow into your system the same way any other data you're collecting does. On the con side of this, it is going to reduce our ability to do analytics because this is really disconnecting the cloud in a lot of ways from the PLC. Those two aren't talking directly, right? So the data is going to both places, but they're not talking directly. And that reduces the amount of configurability we can have inside our vibration system. And I'm going to touch on that a little bit in greater detail in a couple slides here. So there's a big challenge to doing what we just discussed. And that challenge is that IoT systems, by their very nature, are distributed. And that means when I look at a gateway like the one that I've got here, there is no standard memory map, right? That gateway could be talking to anywhere between 1 and, say 100 different vibration sensors. And each of those sensors could be configured to look for different things with different sampling rates, and providing a different number of channels. So there's no way to produce a gateway in this environment that is, that's flexible enough to handle this wide array of possibilities, right? It needs to be able to hold, the gateway needs to hold configuration and data for all those sensors, even if that sensor network changes. And, as a result of this, it needs to support a completely unique map for every installation and a unique set of tags. And that's very countercultural to the way that a typical PLC-based device is designed, right? So in the Rockwell automation environment, in particular, that's what we're focused on today. Configuration space is limited. So we talk about that configurability. Well, we only have 400 bytes of space per gateway to hold configuration information. So that really confines how we do this. Now, we can use an add-on profile. That's a great option that Rockwell offers. The problem with that is that fully featured AOP is going to be static. So if we did all this configuration inside that AOP, anytime a new feature becomes available, that AOP is going to have to be updated. That's not an easy process. And as a result, that's not really the best approach, I feel, for independently enabling flexibility that we're talking about here. So, the focus here that we're going to move to is how can IoT systems find a way to allow PLCs to host configurations and data without sacrificing all of those benefits that we talked about earlier in the presentation. And this may not be the only way, but from here on out, I'm going to focus on how we at Grace have kind of approached this problem and, our solution to that. So the way we've kind of approached this is to not throw away the cloud entirely. So we've built a bunch of tools at the cloud side that give us that ease of configuration for each vibration asset. And we use those. Even if your deployment at your facility is not connected to the cloud, you can use our cloud ecosystem to configure your on-prem platform. And I'll walk through how that's done here. So the first step is you're going to set up or configure each of your vibration nodes. And you can see from these two kind of screenshots here, that's really easy to do. You assign it a name, you tell it, where that thing's going to be aligned relative to the axes of motion of that asset that you're monitoring. And then you set up some stuff like your acceleration range, how often you want it to sample, what bands you're interested in providing data from, that sort of thing. A couple of clicks and you're done per asset. Like literally you could do a network of, 50 of these in a half an hour. Second step is we're going to then map those vibration nodes to the gateways that are going to be used to convey that data to the PLC, right? So this does take a little bit of upfront work. You have to know where that gateway is going to be physically located and then optimize to some extent where those devices are sending data to. So this is a little less intuitive, I guess, to our devices than when they're automatically assigned to a cloud gateway, but it's still pretty easy. So once that map is made, you literally just come into our cloud configurator and you're going to drag each vibration node to the gateway that you want to host that data for the PLC. It's just a drag and drop step. Again, if you've got 50 of these, this step was going to take you, I don't know, less than 5 minutes to accomplish. From there, we're going to export some appropriate files. So if you're using Studio 5000 in the Rockwell environment, we can export either an AOP specific XML, which goes just for our AOP, which is hopefully almost done, in development right now. Or you can export an EDS file and an L5X file, which houses that same configuration information. Two different mechanisms to do the same thing. If you're not using a Rockwell PLC, we can actually export the memory map itself, and we have a configuration tool that lets you apply this. But today I'm focused on what we do inside the Rockwell ecosystem. So once we've downloaded that configuration file, that's going to have all the information you need on your tags, on your data types, everything that's required to really build a PLC-based vibration system, we're going to import that into Studio 5000. And it's literally as simple as these two screenshots. You just go in, you're going to import a component. In this case, it's a program or a routine, and you're going to bring that into Studio 5000 using a couple of clicks. And at the back end of that, you've got tags queued up for that gateway that are going to make that gateway capable of expressing all of that vibration data for all of the nodes that are wirelessly communicating to it, just with a couple of quick clicks. So that really is kind of the end-to-end approach for doing configuration of an IoT system on a PLC using kind of our approach that we use inside the Grace ecosystem. So this is kind of it for the talk. I'm just going to conclude it here with a couple of main bullets. So first and foremost, I just want to reiterate that this is a really important thing in the industrial space right now. 24/7 vibration monitoring can create tremendous benefits for any industrial facility by reducing unexpected downtime, minimizing the maintenance costs of reacting to that downtime, and ultimately increasing worker safety by eliminating a lot of accidents that happen due to reactive maintenance. I want to reiterate that IoT technologies generally are really becoming ready to step into that void and fill that 24/7 monitoring gap. This gives us that ability to deploy balance of plant vibration monitoring across all of the assets in your facility, not just the most critical ones, right? The sticking point there has been, but how do we get it into the PLC? And what I'm trying to bring to you today is that I think we're finally there. There is a mechanism to get that flexible IoT ecosystem for vibration monitoring directly connected to the PLC in a really intuitive and easy way without the need for some expensive or complicated integration effort. So with that, I'm going to close the talk here. We at Grace would love to talk to you about your specific vibration situations and how our technology, or really just that the community's technology as a whole, can kind of come in and help you do better vibration monitoring in a 24/7 capacity inside your facility. I really appreciate your time today, and we hope to talk to you soon.